Yes, the best is in the top floor. Yeah, so we have a coffee break just after, but of course in another way. That's a really the best way to describe it. Both of you speak Spanish. Yeah. Thank you. Last year was that's it. Yeah. Yes, it's last year. It's over. Yeah. Yes, exactly. Yeah, and upcoming conference that this year. Because the deadline.
I found the streaming from your laptop. It's a better quality. Did you check that?
Of course.
Yeah, I found it. It's better than
Use your laptop.
run. You can start.
Yeah.
selecting the one day loading.
So good morning, everyone. So today we have an exciting talk by our second keynote speaker, Professor Carlos Coelho. He did his PhD from computer science from Brown University here in the US in '96, and he's currently full professor with distinction in the evolutionary computation group and with part of the computer science department. He published over 450 papers in international journals with chapters and conferences. He also authored the book Evolutionary Algorithms for Solving Multi-Objective Problems, second edition, and has co-edited the book Application of Multi-Objective Evolution Algorithms. His publications currently report over 52,000 citations, according to Google Scholar Citation versus 69. He received the 2007 National Research Award granted by the Mexican Academy of Science in the area of exact sciences. And since January 2011, he is the national for contributions to multi-objective optimization and constant handling techniques. He's also the recipient of the prestigious award, the 2013 IEEE Master Award, and of the 2012 National Medal of Science and Art in the area of physical, mathematical, and natural sciences. And this is the highest award that the scientists can receive in Mexico. He also serves as associate editor of the IEEE Transaction Registry Computation, Computational Optimization and Applications, Pattern Analysis and Application, Journal of Heuristic, and Evolutionary Computation and the Types of Computing. Keynote speaker.
Thanks a lot. The nice introduction and for the invitation from everyone. So, well, as you will find out in the talk, I'm not really a software guy, I'm an optimization guy. But talking with Marwan about the areas in which I work, some of the work that we have done in evolution and multi-objective optimization may be useful for you guys. Very complex problems from the optimization point of view. So this is the outline of the talk. I will briefly introduce multi-objective optimization, and I will concentrate on hybrid approaches. By hybrid, I mean combining multi-objective evolutionary algorithm with a local search mechanism, at least in the first part. And then in the last part, I will mention another sort of a different type of hybrid called hyperheuristics, in which we combine different heuristics within a single framework using some particular control mechanism. And this is also very interesting, and I believe has also a lot of potential for some of the problems that we're working on. But, okay, the first part of the talk, I will concentrate mostly on what is called a multi-objective numeric algorithm that combines a search engine, which would be a multi-objective evolutionary algorithm, with a local search engine. And for this, I will discuss both discrete search spaces and continuous search spaces. Okay, so multi-objective optimization, I believe you are already familiar with it. It refers to solving problems having two or more objectives. Normally, the interesting part here is that these objectives have to be conflicting. Because if the objectives are not conflicting, then solving the problem is really easy, because you can optimize each of the objectives separately. You will find a single solution, and this single solution is all you aim to find. However, when there is a conflict, then even the definition of optimality becomes tricky. So this is the definition. We have k objectives we are trying to optimize, and perhaps additionally the problem also has constraints, inequality, or equality constraints. So the notion of optimality that we normally use in multi-objective optimization, although it's not the only one available, was originally proposed by Francis Cicero Edgeworth. He worked at Oxford University, and in 1881 he published a book called Mathematical Psychics. In this book, he refers to this sort of intuitive notion of a trade-off solution, in which he tries to find the best possible between two objectives that are in conflict. However, this concept was generalized by this guy, the Italian economist Alfredo Pareto, in a book published in 1896 called Cours d'Economie, it's a book in French. And in this book, his notion, which is now generalized for any number of objectives, is called optimality. However, over the years, people changed the name, and now it's called either Edgeworth Pareto optimum or simply Pareto. The most common. As I said before, this is not the only notion of optimality. For example, the Russians like to use something that is called Gradier's choice function, which is somehow equivalent to Pareto's notion as well. But this is the one that most people do. So if we are assuming we are minimizing all the objectives, and it is always possible to do this sort of transformation, we say that a vector of decision variables that is feasible, that means it fulfills all the constraints, is Pareto optimal if this condition holds. If it's less equal for every objective and strictly less for at least one. There are variations of this definition if we remove the second part and we only keep this one. This is called weak optimality, and it will produce more solutions than the original definition of Pareto optimality. If we remove the first part and we only keep the second, this is called a strong optimality, and we will get less solutions. So in some cases, people are interested in variations of this definition. So basically, the definition is the reason why we get several solutions, because if the objectives are conflicting, then because of the definition, we are going to get a whole set of solutions. This is called the Pareto optimal set. And this is defined in decision variable space. There are many confusions in terms of the terminology. Strictly speaking, the vectors that correspond to the solutions contained in the Pareto optimal set are non-dominated, but people use the term again. Which, strictly speaking, is not correct, but it's fine. And then the image of the Pareto optimal set, that means the objective function values that correspond to these decision variables, is called the Pareto. If you ever look at some paper on IMO, people develop these algorithms, you will see that they are, well, we are pretty much obsessed with the Pareto. Geometrical shapes that look really ugly, very disgusting, and then we try to produce all these complicated Paretofrons to test our algorithms. And people sometimes, they ask me, are these complexities of the geometrical shapes of these Paretofrons related in any way to the complexities of real-world problems? Of course not. They are not. Because we are computer scientists, we are trying to build complicated algorithms, even if these complicated problems are not. And the real complications of problems are lying somewhere else. And some of the techniques I will explain today are more related to these complexities than these specific. So before evolutionary algorithms were used, of course, people were already solving multi-objective optimization problems. But in the 70s, people in operations research started developing mathematical programming techniques. And of course, in multi-objective optimization, we have linear multi-objective optimization. There are specific algorithms for that. We also have something that is called multi-objective combinatorial optimization. And we have specific algorithms for that. I normally refer to non-linear multi-objective optimization, but when I talk about discrete local search engines, I will be touching a little bit on combinatorial. So if there are so many algorithms already available for solving multi-objective optimization problems, why do we need heuristics? Well, there are several reasons. The main one from a mathematical point of view is that the general nonlinear multi-objective optimization problem, we cannot have any algorithm that guarantees convergence in every case. Also, in practice, the currently available algorithms have several limitations. For example, most of these nonlinear multi-objective optimization techniques generate normally a single element of the Pareto each time you run the algorithm. Also, most of them are very sensitive to the shape and the continuity of the Pareto front. For example, if the Pareto front is disconnected, some of these techniques don't work. Some of them require the first and even the second derivative functions, or probably also from the constraints. So, in contrast, evolutionary algorithms are less sensitive to this shape of the Pareto front. Also, if properly manipulated, they can generate several elements of the Pareto optimal set in a single one. And also, since they have a population, most of them at least have a population, they can operate with several solutions at the same time, which makes it possible to generate several different elements of the Pareto optimal set in a single one. However, the main disadvantage of evolutionary multi-objective algorithms is the computational cost. It becomes an issue in some cases because they normally require to perform perhaps thousands of objective function evaluations in some applications, such as in aeronautical engineering, for example. If you have a very expensive objective function, it may be algorithms have been developing in a sense to try to overcome somehow this issue. Get to multi-objective numeric algorithms. So first I'm going to give general concepts on this, and then I'm going to talk about approaches that were developed for discrete search spaces, which is very intuitive when you try to develop a local search engine, because if you have a discrete search space, defining a neighborhood structure is very intuitive. Continuous search spaces are tricky. It's still possible to design a local search engine. It's straightforward. It's complicated. To mention some applications before I move. So memedic is a term that was that has its roots in the work introduced in his book. The Self-15 is a very famous. And he defines the word mean as an imitation unit, and he postulates the possibility of cultural transmission. He will provide in recent editions of the book a simulate of this, of how culture could be transmitted in a genetic way, you want to call it. He uses this to pose the idea that cultural evolution is possible, and that it will be possible to have cultural evolution in contrast to we are more familiar. In the 80s, in the late 80s, Pablo Moscato, who was at Caltech, he released a technical report in which this concept of memedic algorithm, any sort of algorithm in which we use a population and combine this with the global search engine. Some people didn't like this because they say that we have been doing this before, this guy just gave a name. Fine. It's okay, you may call it something else if you want, but this is the concept. So the idea is really very simple. You have your particular, in this case for multi-objective optimization, you have your multi-objective evolutionary algorithm, and at some point, you apply local search. There are, of course, some issues related to the application of local search, and actually, perhaps there are more issues than you could think of at first sight. So, for example, the first question is, how often do we use the local search engine? You normally don't want to use the local search to every single solution because that would be too expensive and it may be unaffordable. So how often should we do it? For how long should we apply the local search? Normally there is a trade-off because the global search engine is already computationally expensive. If you add local search, it will be more expensive. So is it worth it to apply, for example, 100 evaluations, which is costing me perhaps 20 minutes? It's only 0.1%. Is this okay? Should I apply the local search for a shorter time, for a longer time? This is very important. On which solutions should we apply? To the best solutions, to the worst solutions, to any solution, to every solution. How efficient should be local search with respect to its effectiveness? So is it okay to perform 5% more evaluations if the improvement is less than 1%? It is acceptable. In some cases it is, but this is something you need to figure out. How should recombination and mutation interact with the local search engine, if they interact at all? Are we applying the operators with the local search or not? And finally, and this is more an evolution interpretation question, what sort of fitness assignment scheme should we assign? There are two of the two main ones, which are called Lamarckian and Bernoulli. The Lamarckian scheme is the traditional local search. You have a base solution. This is the first, the Lamarckian. In the second one, you do the same, but in this case, you don't replace the base solution. You only modify its fit. Because in the neighborhood, there is a better solution. But you allow somehow the diversity by not replacing the base. The second approach is less common. Most people use the market. A local search engine has been analyzed by some people, for example, Bill Hall in 94. He analyzed these questions, but in the context of single objective opinion. It is possible in some cases, but all this is thinking in discrete search space. If you move to continuous, then everything gets very ugly and complicated. So most of the original multi-objective numeric algorithms available in the specialized research, they were all designed for discrete search. So, for example, by in the 90s, mid-90s and early 2000s, people like Joshua Knowles proposed different mimetic variations of well-known algorithms. For example, the Pareto-Archive evolution strategy has a mimetic variation, not very well known. It was published in the year 2000. Also, Hisauchi, in which he developed a very interesting algorithm called the multi-objective genetic local search. And there was sort of an improved version of this algorithm by Jaskiewicz in 2002, published in the article Transactions from Evolutionary Computation. And there is even a survey at that time, published by Joshua Knowles in 2004, in which he provides sort of a state-of-the-art review of multi-objective numeric algorithms. Most of them focus on the discrete search. Some of these approaches, for example, the one proposed by Ichibuchi, which has several variations. This is one of them, the simple multi-objective generic local search. In this case, basically, what he does is he uses a weighted aggregated function. In the aggregated function, you are adding all the objectives, and you are multiplying each of these objectives by a weight. And these weights are variated, and he uses the best solution. He determines the best solution based on a local search that he performs, and this local search is modified at each iteration of the algorithm. Then he produces several variations of this. He modifies the local search engine. He modifies the local search is applied, and so on. So, for example, in this case, the local search only applied to the solutions that are close to the parents in objective functions. All these variations were motivated by the aim of improving the performance in a particular domain. He was trying to solve some scheduling problem. In 2003, he compared the use of a local search engine based on this original scheme with just the weighted with the use of Pareto dominance. evolutionary multi-objective optimization from the mid-90s up to perhaps the year 2005, 2006, people didn't like aggregated functions. Even today, people don't like aggregated functions. But in the mid-90s, even early 2000s, if you had a paper submitted to a journal social dialectical transactions and evolution computation, in which you mentioned in the abstract that you were using an aggregated function, the paper would get rejected. Nobody wanted to know about this. Because the dogma was Pareto dominance is better. So you should use Pareto dominance. Some people who were working in combinatorial optimization, they were able to show that using weighted aggregating functions in certain domains, particularly in combinatorial optimization, produce better results than Pareto. That important for some people, but it sort of kept the notion that Pareto dominance is not really a universal mechanism for solving multi-objective optimization problems, that there are other ways. And that's one of the reasons why now algorithms based on decomposition, such as MoIA-D or MSGA3, are very successful because they can sort of deal with all these issues in a more flexible way than Pareto dominance. So this was a very important result. It was published in the Dialectical Transactions on Evolutionary Computation because it showed that it was still possible to use a weighted aggregating function in a time in which nobody was using them, but if you were solving this particular combinatorial optimization. So in his case, he used knapsack and scheduling problems. There were also other interesting applications. For example, this one from the University of Illinois, the non-dominant sorting memetic algorithm, which was coupling the original NSGA from Talia to a local search engine that uses Baldwinian learning, and this was used for a aerospace application. And this was, I believe, a master's thesis. There were other studies in which people use, let's say, more exotic approaches. For example, this one, using a multisexual genetic algorithm. This is a nice idea proposed by Liz and Ivan that nobody really used much over the years. The idea here is with the multisexual genetic algorithm, each individual has an extra gene or an extra bit, if you want to call it that way, that denotes gender. So for recombination, they only allow recombination but that have different genders. So this is something that we call a restriction to recombination, and it's called mating restriction in evolutionary computation, and it's normally aimed to modify diversity, either to decrease diversity or to increase diversity. In this case, the purpose was to increase diversity. So they use this approach, and they use simulated annealing as the local search engine, and there were several variations. All these variations is basically trying to find this balance between the local search engine and the global search engine. And finally, the last one, that only applies local search to the non-dominant solutions that were produced at the very end. Search at the very end, and this is the one that works best. In this case, they are also solving scheduling problems. These are people from Argentina. Then is the memetic version of the Pareto archive evolution strategy. The original algorithm is a 1+1 evolution strategy. It's a very simple algorithm. This memetic variation already has a population, so it's bigger in terms of the number of solutions it adopts. And it also incorporates crossover because the original Pareto archive only has mutation, has no crossover. And the interesting part of this algorithm is that it uses two archives. One keeps the local non-dominant solutions. That means the non-dominant solutions found during that iteration of the algorithm. And the other one keeps the global non-dominant solutions. That means those solutions that have been found to be non-dominated over all the iterations or all the generations. And then it provides mechanisms to move solutions from one archive to the other, from the local to the global. So it has other interesting aspects. For example, it constrains the search to a certain allows the algorithm to reduce some of the solutions that have been generated. So it's an interesting algorithm. However, it was not developed for a specific application. At that time, it was tested with the knapsack problem, which Eckhart Sitzler had used with the strength Pareto evolutionary algorithm, the SBA, and that's the reason why they compare results with respect to the SBA. However, there is this paper that not many people know about, from Joshua Knowles from 2002, in some conference, the Flourishing conference on artificial intelligence or something like that, in which he analyzes the details of the fitness landscape of a particular multi-objective combinatorial optimization problem. In this case, this is very interesting because very few people at that time were trying to do that. Normally, they will, empirically try different local search engines, produce arbitrary neighborhood structures, not using any information about the problem itself. So this was very interesting, more scientific in a way, because he first tried to analyze the properties but very few people follow this path, unfortunately. So there were many others. For example, some people use this for designing circuits. This guy from Japan, he used this to improve diversity. All this idea of using local search. Kleeman in the US, notion here is that using some specific information from the domain, you can focalize the search to some particular regions in which you need more locals. This, however, in general is difficult to do because for you to have this information about the domain, you normally need to perform many objective function evaluations. Useful information. Just Kiewicz improved the algorithm proposed by Ichiguchi, and he published this around the year 2002. I refer to the original MODLS. And basically, the trick in this case was to increase the memory usage and decrease the local search. But he was still using a weighted utility function, that's an aggregating function, with he also tried a Chebyshev utility function, which is what decomposition methods use today. And he produced very good results, similar to those from Ichiguchi, but at a lower computational cost. However, as I mentioned before, the memory use increased, and it increased in an important way. So he used, for example, this is something very common in operations research. He used quadtrees to store the non-dominant solutions obtained by the algorithm. People in IMO today, they are not very fond of using sophisticated data structures to store the non-dominant solutions. But in operations research, they have done this for a long time. Since the 80s, at least, they have used, for example, quadtrees, because it's very efficient to retrieve non-dominant solutions, particularly if you have thousands of them, using these data structures. Also, some people in IMO have used the red-black trees. So there are other data structures possible. And well, in this case, he compares with other multi-objective statistics. For example, this one, MOSA, is simulated annealing, proposed by Ulungu in Europe. And not only in the original problems that Ichiguchi adopted, but also in multi-objective instances of the traveling salesperson problem. And obtained very good results. Then in 2003, he undertook a very comprehensive comparative study of different meta-heuristics using the knapsack problem. So to compare the memetic version of the Pareto archive with another version of multi-objective simulated annealing. All these three are versions of multi-objective simulated annealing. This one by Sisek, also Jaskiewicz is the co-author. and then his own multi-objective genetic local search. And some interesting things, for example, the mimetic version of the Pareto archive evolutionary strategy, which is the only one from this set that is based on Pareto dominance, is able to converge to the true Pareto front, but the distribution of solutions that it produces is not good at all. And he finds the others his conclusion is, again, as Ichibuchi, saying as Ichibuchi, that aggregated approaches are better than Pareto ranking in multi-objective combinatorial optimization. And then his last study, because after this guy got lost, I haven't seen any papers of him in a long time. In 2004, he compared 10. The previous study was 5. So this is more comprehensive, and he includes now this elitism. This is called constrained elitism. It's a version of the NSGA. The original NSGA, the SBSE from Sicily, and another along with multiple objective, multiple star local search, and the PMA, the Pareto mimetic. This is a very comprehensive, ambitious study. And in this paper, he uses a different problem, the bioobjective set coverage, which requires a special matrix encoding. So this is a more objective genetic algorithms, for example, Dandiblo in France. He developed an approach that is very, very strange. He combines many things. He starts with a genetic algorithm that uses non-dominated, keeps only non-dominated solutions. Then he applies a mechanism similar to what Vega does. Vega is the oldest multi-objective evolutionary algorithm with a very simple idea. What it does is it takes the population of a genetic algorithm, divides the population into as many objectives as you have. Normally, it was only with 2 objectives. So in subpopulation 1, you select the best solution with respect to objective 1. Subpopulation 2, you select the best solution with respect to objective 2, and then you do the recombination of the individuals from the 2 subpopulations. The aim is, if I combine the best in objective 1 with the best in objective 2, the offspring should be some sort of fate. But same as in life, this doesn't happen all the time. Because what he was doing is to apply a linear aggregate function again. But his notion of who should be selected goes against the definition of Pareto optimality. In Pareto optimality, you want the best possible trade-off. If you only select the very best, you are selecting the extremes of the Pareto. So, and you are leaving on the middle to a random search, which is what Vega does. But well, he used this, and then he applied a mechanism from the MPTA, which is also a null algorithm from 1994, and then he applied local search. It's a very sort of complicated approach, but he claims this was nice and it worked nicely to solve these cases in which, as I said before, it's very intuitive to have a notion of a neighborhood structure. But what about continuous optimization? What happens if I have a continuous optimization problem and I want to design a local search? Well, this is very tricky. Apparently, this paper from 2001 by Gold and Dead is the first attempt, and this should be 2002. Seems to be the earliest and they solve this problem of designing engineering checks, which is a very interesting problem, computationally expensive, because these checks have to be analyzed in a final element analysis software. And first, they apply local search after completing all generations, but in a further version, they do it after each iteration. and to every individual, which is, of course, very expensive. In this case, although the problem is continuous, the shapes are handled as discrete. So the neighborhood structure is not that difficult in a sense. So that's the trick. Although the encoding is with real numbers, the actual domain in which they are solving the problem is discrete, because the shapes are like boxes, like pixels in an image, and they try to optimize the components of these cells. So this is discrete in a sense. Then Yao Shujin proposed this very interesting idea in a paper in 2001. He was using this dynamic weighted aggregation function. This was very interesting. At that time, in 1994, this paper came out. Like, the general notion was, you're not supposed to use linear aggregation. Why? Because it's possible to prove that if the Pareto front is not convex, then you cannot generate the non-convex portions of the Pareto front, regardless of the values of the weights. Whatever weight you use, you cannot do it. So Yao Shujin proposed this Pareto front using polar coordinates. And then he showed it was possible to generate the non-convex portions of the Pareto front using a linear aggregation function. It's just he was in a different certain space, of course, but he could do it. And then in 2001, he proposed another variation of this algorithm, in which he showed that it was possible to extend this to more than 2 objectives. Property he called connectivity. By connectivity, he referred to problems in which the decision variable space and objective function space are both connected. And he showed empirically how this property could be validated. And he said, well, if this property holds in continuous surface spaces, then it is possible to define a neighborhood structure. Why? Because I have no holes when I move, right? So I can move along the Pareto front, for example, because I know the Pareto front is connected. The thing is, in practice, it's not possible to know this ahead of time. You don't know if the Pareto front is connected or not, unless you know the true Pareto. But it was an interesting notion. In combinatorial optimization, in single objective, there is a very interesting property called global convexity that some people have studied since the 90s. Global convexity means that, and this happens only in some combinatorial problems, that solutions reside in a specific, normally a small region of the surface space. So, if you can get to that region, in whatever direction you move, you will be finding all the time very good solutions. Some heavy metal heuristics were designed to explore this. For example, glass was designed to explore global convexity. But this property, as far as I know, it hasn't been shown that it exists also in multi-objective. We know it exists in single objective. Multi-objective, that we will know. So other people develop local search engines in a very clever way. They say, okay, I'm dealing with a continuous problem. I don't know anything about neighborhood structure. What if I use a mathematical planning technique? Okay, that's possible, of course, because mathematical planning techniques in single objective optimization, they are designed somehow to perform a small movements as local search engines. So, for example, in this case, you use Rosenbrock's algorithm, which performs very small movements in continuous search spaces. This is using a local search engine, and you don't have to worry about the neighborhood structure because the algorithm already takes care of that part. He also used this Pareto domination multi-objective simulated annealing as the global search engine. So there were many others, for example, based on differential evolution. Massimo Basile, he developed some hybrids between evolutionary search algorithms and multi-agent strategies. These multi-agents are the local search engines, and he used this is more tricky. In some space. Normally, it's in objective function space, could be also in decision variables. And this guy, Sinja, who was in Finland, he proposed a combination of NSGA2 with a reference point method, the predecessor of NSGA3, because NSGA3 does exactly that. And he showed the use of reference points that speeds up convergence. Other people tried to do the same. So the motivation in continuous search spaces was different. In this case, people were trying to speed up convergence. When applying the local search, they wanted to see if the algorithm, the multi-objective evolutionary algorithm, was able to converge faster. And several people play with this idea. For example, Adra, who worked with Peter Fleming, has 3 different local search engines with a multi-objective generative algorithm originally developed by Fonseca. He used simulated annealing, and heap climber, and taboo search. All of these are really for combinatorial optimization. If you use a binary search space, apply this engine. Elizabeth Banner used approximations, again, a mathematical planning technique. They use NDI. Which normally they move into small steps. That's a local search. Not very creative. Mathematician, how would you do this? Well, the problem is being able to do the structure. Objective optimization, the gradient gives you the best possible descent direction. This will not. What about multi-objective optimization? Let's say I have 2 objectives of objective 1, and this is the best descent direction from the perspective of objective 1. Then I get the gradient of objective 2, and this is the best descent direction from the perspective of objective 2. Well, the problem here is, this problem is also multiple. What I will get is a cone of descent direction between all the gradients. In this case, gradient 2, but you may have 4 gradients. And this cone, possible directions to move. And the question is, which is the direction I should use? This is the best possible direction. It's just within these 2 boundaries, if I'm using 2 gradients, I don't know what the best solution is. And the thing is, nobody knows. There is no analytical way of knowing. You need to develop some approach to do this. So Bosman, in 2005, was the first to identify this as a multi-objective problem. And he proposed a way to find a solution which is very empirical. This is not really based on any properties of the search space, but it sort of works. And there is another issue if you use the gradient. As I said before, the motivation is you want to speed up convergence, right? You want your algorithm to run faster. But you also want to keep low the number of objective function evaluations. Otherwise, this is going to be too expensive. If you approximate the gradient using, for example, finite differences, you're not going to reduce the number of objective function evaluations. You're going to increase it because you normally require many evaluations. So the trick here is people who work in this area, and we did some work on this some years ago, called automated differentiation. It's a technique in which even if you increase a lot the number of decision variables, the number of objective function evaluations increases only linear, not exponential. And you can keep low the number of objective function evaluations. This is nice as you increase the number of decision variables. So it's a trick you can play for estimating. So this is Bosman's approach, was one of the first. he basically performs some matrix operations, solves a linear optimization problem, and then he finds the descent direction. And also you need to find how far are you supposed to move in that specific direction. So he proposed this combined objective repeated line search, and he proposed an improvement in 2006. In this case, he uses what we call an estimation distribution. It's an algorithm in which we use a probability distribution to emulate or simulate the behavior of the operators of an evolutionary algorithm. And that's because this guy was in that area. So we use this to do the estimation and to find the proper descent direction. But that's not the only way. Other people try different things. This guy, for example, he used the gradient, but still used sequential quadratic programming. He coupled this to NFGA2 and SPA. And he found something that is very intuitive that it will happen, that if there are no, for example, no local Pareto fronts, but with local Pareto fronts, gradients cannot be. Because gradients will get trapped in the local Pareto front, and it's not going to work at all. Other people propose other ideas. For example, Harada, he proposed this Pareto descent method, which is a different way of solving the same problem that Bosman was trying to solve. In this case, he again he assumes no local Pareto fronts because local Pareto fronts are attractors for the gradient, so the approach is not going to work in that case. And he uses also sort of a simple idea to produce the descent direction and how far should we move. This is more, I would say, empirical, more empirical. Brown and Smith also analyze this concept of the descent cone, which is conformed by the intersection of the what we call the negative half spaces. These are the directions generated by the gradient. And he also studies, he provides a really nice study of the problem. It's just, he doesn't propose a nice solution. He only sort of explains, this is the problem you have, and you have to deal with this. It's very useful if you want to do research in the area. It's just that he does not propose the actual solution. The state. Many other people work on this. For example, this guy, he's an Indian guy who was with Kalyan and then moved to Germany and got his PhD in applied mathematics. He used stochastic gradient, which is another possibility. However, the stochastic gradients have also some limitations. For example, again, the local Pareto fronts, ZDP has, ZDP4 has several local Pareto fronts, so it doesn't work at all in that case. But in other cases, it provides competitive results. We also work on this. We propose this hill climber with side step, the HCS, which may use gradient information if available, but if it's not available, we can estimate it, and it still works. And it's a nice algorithm. It uses the geometry of the cones to define the best descent direction, and it uses a very simple procedure to estimate how far should we move. So it's a very nice algorithm. And when we were working on this algorithm, we stepped into a very interesting problem that we published in the Electric Transaction Solution in 2012. But many people got very angry with us because of this paper. What we found is the dogmas in NEMO. NEMO, one of the dogmas is, as you increase the number of objectives, when you get to the so-called many objective optimization, nobody knows really what many means, but most people will tell you it's 4 or more objectives. That's many. Because Pareto ranking doesn't work anymore. If you keep the same population size, you will have to increase the population size a lot. So one of the dogmas is just scalability by itself. That means increasing the number of objectives by itself makes the problem harder. What we found when studying the cones, and this was by accident, is that this is not true. That the actual source of difficulty is not the scalability itself, but the intersection of the same cones. This is the real source of difficulty. And we were able to show that in some cases, you can increase the number of objectives and Pareto ranking still works. and in others, even in low dimensionality, because the complexity is really related to this intersection of the same cones, which makes more difficult or less difficult to solve the problem. However, when we try to publish this, people wanted to kill us because many people were profiting from many objective optimization. Like, why should we say that the scalability is not an issue? It's the biggest sin. And that's the reason why nobody reads the paper, nobody cites the paper, but that's fine. It's okay, only Chiguchi does. But it's true, we found this. We cannot claim this is the general case, of course. But we found that this happens in these problems that cannot be properly solved. So many objective doesn't seem to be by itself a problem. Another possibility, if you don't want to deal with gradients, is to use direct search methods. That means optimization methods that don't require gradients. So we work on this with Nellen and Mead's method, the golden section, and other approaches, who gives as well. And it's okay. I mean, of course, the results are not as good as when using gradient systems, because these methods have more limitations, they are less powerful, but we still were able to reduce the number of objective function evaluations that the original multi-objective evolutionary algorithm was producing. So we also use surrogates, this meta model based on support vector machines, to reduce the number of objective function evaluations, because we were trying to solve some expensive problems in aeronautical engineering. And all of this was done with decomposition method in the algorithm, which is very famous. So some examples of cases in which approaches have been used. Inventory control, most of these are discrete problems. Operational strategies, the energy system of a building, parametric optimization of a housing filter, traveling salesperson, and routing in urban public transport. However, there are many other applications, of course. They are mainly intended for discrete search spaces, but as I showed, it is also possible to use them in continuous search spaces, because as the only requirement is that you find some approach that can be used as the local search engine. The global search you already have, NSBA3 or MOIAD or SPA or SSBSE, whatever algorithm you already have. If you want to know more about this topic, there are a few papers available. There is even a book co-authored by one of the invited speakers. And many recent students in the last few years. I haven't seen the most recent is this one from 2012 in the handbook of numeric algorithms, but I'm not aware of anything more recent than me. So, okay, the last part, hyperheuristic. Hyperheuristics are a very intriguing, very nice idea. Here, what people try to do is to combine different types of heuristics with the aim of combining their advantages. So one of the prerequisites is these heuristics that you put in this portfolio are supposed to be somehow complementary. In the same day, not fun to do this because it's going to be the same to use any. They have to be complementary in a way. One may have difficulties in certain types of problems, the other one may do better. And because of the no-free launch, this is supposed to happen with every heuristic. It's just you need to find out who is good for what. So the idea is to have a more general search engine that can solve a wider variety of problems. And again, hyperheuristics were proposed in the specific context of combinatorial. Because in there, we know better how heuristics behave. In continuous search spaces, it's not that well known. However, there are some attempts for continuous search spaces as well. And here, hyperheuristics for multi-objective precision are not very common, but I will mention a few. So Edmund Burke, who is the guy who proposed the notion of hyperheuristic, he extended this approach, which he uses reinforcement learning. And he used this in a multi-objective optimization problem. In here, he uses what these low-level heuristics based on some scores that he computes during the execution, and then a multi-objective framework to couple all these low-level heuristics and solve this space allocation and time taking problem, this discrete problem. This nice. Kumar, he uses genetic programming to evolve different heuristics, and this is a more recent research trend. Instead of providing the specific engine to do the local search, people are now using genetic programming to design heuristics based on very simple rules for this particular problem. This is relatively easy to do in discrete search spaces. It is more tricky for continuous search spaces, but this is still possible. So again, you need to have some sort of reward system in which a heuristic that does better gets a higher fitness and gets to perform more iterations. Other approaches, in this case, they use a heuristic selection method model as a Markov chain to solve a very well-known benchmark in EMO, the DTL set test problems. This is one of the few in which they solve continuous multi-objective optimization problems, again, based on reinforcement learning, which is some sort of approach. And he keeps this set of weighted edges that represent probabilities of moving from one heuristic to another or transitioning between them. This is another one in which they use annealing, different low-level heuristics for a more real problem. Is the electricity distribution networks. You want to do the power compensation problem in these electricity distribution networks. And in this case, they have 6 low-level heuristics within the hyper-heuristic. The idea here is that the engine has to decide when to use a particular low-level heuristics and for how long. And this is the difficult part. Not only gathering the heuristics, but deciding when to use it. So in this case, simulated annealing is this decides when to use each of these low-level heuristics based on the dominance between the new solution that is produced by them and the solution that has been stored, this archive solution. We have amalgam by Brook and Robinson, which can be seen also as a hyper-heuristic for continuous multi-objective optimization. And in this case, again, they use several population-based multi-objective approaches, and they decide the solutions that are produced by each of these low-level heuristics is decided proportional to the percentage of the previously created individuals that remain in the working population. Next one, I think you know this guy who gave a talk this conference, Patrick. They propose Borg based on these characters and structure. It's a multi-objective evolutionary algorithm that combines also several mechanisms, including epsilon dominance, which was used a lot back in the early 2000s. Also, a measure of convergence is called epsilon progress, randomized real stars, auto-adaptive multi-operator combination. All these within a unified optimization framework that again aims to adapt somehow all these low-level mechanisms to have a more general framework for solve a wider variety of multi-objective optimization problems. But in this case, rather than combining all mechanisms, he's basically combining operators, which is another possibility. And from my point of view, this can be seen also as a hyper. So, what remains to be done here? Of course, there are many things regarding applications, either of the multi-objective magnetic approaches or the hyper-heuristics. In continuous search spaces, not much more has been done. Also, I haven't seen that many parallel hyper-heuristics for multi-objective optimization in particular. I have seen a few, 2 or 3, but not that many. Hybridization with direct search methods, of course, and the balance between global and local search. These, of course, these studies we can do, for example, with benchmarks, but it will be a lot more interesting to do this in a particular domain. For example, many years ago, people were doing a lot of software testing with generic algorithms. If we use a specific domain, then I think it will make much more sense to analyze this balance between global and local search in a multi-objective memory data. This is just to give you an idea of the growth of the field, the EMO field. In here you can see it looks small, but this is the year, publication year, and this number of publications per year. So it all started in 1984. There was only a PhD thesis. In 1985, there were 2 papers by David Schaefer, both of them. He got the award of the pioneer in EMO. Then in the 90s, it started very slowly. In 95, Carlos Fonseca published the first survey on EMO. And at that time, it was possible to claim, I have read everything on 30 papers, do 3 PhD theses. In 99, I published the second survey on EMO. And I could still claim I have read everything on EMO. It was 100 papers, 5 PhD theses, or 6. Mine was on the 3 or 4. I woke up, and everybody was doing EMO. So what the hell is going on here? Everybody, even people I have known for years. Some of them even told me they didn't like EMO. I swear to God, they told me that. And now they are doing EMO. I said, so what's going on? Why is that everybody doing it? Which is good for us, of course. We reached a peak of 1,000 publications in a year. And then some people ask me, well, there is a decrease here in the interest in EMO. No, not decrease in the interest. There is a decrease in my time. That's why I don't have that many papers here. I still believe people are doing a lot of EMO these days. It's just I don't have time to keep track of all this work. But it's there in every domain. And I think people will continue to use EMO because many problems in real-world applications are somehow multi-objective. So I believe the use of hybrid approaches, and by hybrid you can use anything you want. It is not necessarily local search. You could combine, and this I didn't include in the talk because of time limitations, but you could also combine different multi-objective evolutionary algorithms. The whole algorithm, not just the low-level part. And some people have done this, but it's not very common. And there has to be a specific motivation unless you want to play with a crazy idea. But most people will do it for a particular reason, to combine, for example, to use, let's say, energy A2 for a time and then replace energy A2 by EAD. Doing things like that is also sort of a hybrid approach. So there are issues, of course. I already mentioned the main ones, and all of them, they require more research. But for me, the important question is for some people, particularly on our side, the meta-heuristics side, they believe, single objective optimization, that the future of meta-heuristics is hybridization. Today, we're living a time, I don't know if you're aware of this, but people have been proposing in the last few years some really, really crazy meta-heuristics. Relying on gravity, Big Bang, and there are many of them, many. There are even books now about all these new meta-heuristics. And many people in this community have been criticized because of that. And as I mentioned this year at GECO, at the Evolution Computation in Practice track, that the problem is, once you look into the details of many of these new meta-heuristics, it turns out they were exactly the same as differential evolution. But they claim a different, to have a different biological metaphor and all this. This is taken as nowhere. So people believe that we already have a sufficient number of nice meta-heuristics that is the hybridization because of the limitations imposed by the no free lunch theorems that say that no single heuristic can be best in all types of problems. So if this is of course true, and the proof is true, then the way out is to combine. If we combine and decide to use one particular meta-heuristic during some time and then replace it by another one, when the problem has a different feature, different characteristics, or the fitted landscape has different properties, then this should take us, for example, with the hyperheuristics, to a more powerful search engine that we can use in a wider number of applications. So we believe, some of us, that in evolution of multi-objective optimization doesn't have to be different. That it's pretty much the same thing, that we need to move in that direction. And one important step is local search, but that's not the only one. I believe hyperheuristics are as important as local search. However, if you guys work in combinatorial optimization, local search may be very useful. Coupling this to a multi-objective evolutionary algorithm, and there are not that many papers in that area. So you want to know more about EMON? There are many books, but I only get royalties for this one. So this is the only one some people ask me, because this is the second edition, which almost cost me a divorce, and they ask me if I'm going to go for the third edition. I will get divorced first, and then I may do the third edition. But now we're really thinking of having a second volume, because having a third edition would be very difficult. This one was already very difficult to negotiate with Springer. I don't know if you have negotiated with a publisher, but they are tough. It's tougher than my wife to negotiate with the first edition was very expensive. It cost like $150 because it was published by Kluwer, and the price was in euros, in a time when the US dollar was higher than the euro. Then the euro went up, and the price went up a lot, and we were very upset about that. So before producing the second edition, I negotiated with the Springer, because now Kluwer had merged with the Springer, and I tried to ensure that the price would be less than $100. And it was $99. Less than $100. It was fine. But they said, well, we will do it with one condition. You are not to exceed 800 pages. I said, okay. So at some point I realized, I think the book will have more than 800 pages. So I asked them, what do you mean by 800? Is numbered pages or total number? And this is not computable for a publisher. They never expected me to ask that. So they say, okay, numbered pages. So the book has about 1,000, because some of them are not numbered, but it has 800 numbered pages on it. I sort of kept the constraint. But it was very difficult. It was a lot of work, because the first edition was in 2002, and from 2002 to 2007, the field grew so much. Now, from 2007 to today, it has grown a lot. That's why we're thinking of a second volume that only focuses on things like hybrid algorithms, many objective optimization, scalability, and decision level space, other issues, rather than having a whole book, which would be a lot. You also, if you're interested, you are welcome to visit the EMO repository. This is a website. It looks like the image, but in this website, you're going to find all kinds of information, including a very large database of bibliographic references related to EMO, about 300 PhD theses, many papers. For a few of these papers, we provide a link when it's possible to do that. Also, contact information of several EMO researchers, and what many people find useful is public domain implementations of many algorithms. We also have whole libraries like JMetal, for example, which provides many multi-objective evolutionary algorithms in Java. And there is a more recent version of this platform that is called CPP Metal, in which we have the C++ versions of many of these algorithms, including some algorithms that were developed by my research group. JMetal was developed in Malaga, in Spain. But they have incorporated several of our algorithms. And I have to say, some of their implementations are better than ours. So we claim it's our algorithm. Their implementation, because it works better, is fine. I can complain about that. Also, they have proposed names to our algorithm, which is also very interesting. We propose a multi-objective particles one optimizer that is called OMOPSO, because my student is not very creative. She didn't know what name to use. So O really stands for hour, But I told her never to mention this in the paper, and we didn't. So these guys from Spain, when they implemented this algorithm, they asked me, so the O means optimize? Yeah, sure. You will find it with a different name. That's not what we meant to do in the original algorithm, but yeah, it's fine. So all this information is there, and the database is very large. You will find a pressure for your specific areas. You will find papers there that may be interesting. And also a few PhD theses. We collect PhD theses from all over the world. We try them to be in English, but not all of them are in English. Most of them are. And some of these theses are quite interesting. They refer to some very specific topics in all areas you can imagine, including, of course, software engineering and software development. So that's all from my part.
Yes, we have time for questions. 1 minutes. Okay, let me start with the first question. So, yes, great talk summarizing most of the studies. So my question around hybrid approach, because I know software engineering using it in different ways. So the first one, trying to solve the same problem where they're using the local search to look for maybe some come up with new solution that they can maybe document that in the local search. So they're still trying to solve the same problem, but with the process in two steps, global search to look for set of results and local search. Define it, define it again. And the areas where they're trying to solve two different problems using global and local. So, like as you mentioned, the hyperlinks, where, for example, in the test-based generation problem for software, they try to use hyperlinks to find the best time of the algorithm to find the right test case. So, do you think that this hybrid approach is more appropriate for one problem or maybe the efficiency that you guys two different problems or what's making it
different? Normally, I believe the aim is like the first type of problem you mentioned, in which you have a very large search space. For the global search, they put you in some specific region, which has good solutions, and then you refine the solution. Trying to tackle two different problems, I believe, is more common with coevolution. Coevolution normally does that. If you have one search engine, it's normally the same, you're using two coevolution languages, but one part is trying to optimize in one direction, and the other part is trying to optimize in a different direction. How to find a trade-off between these two types of solutions. You want the solution to be constrained in a sense, in one parameter, you can research it, and the other one try to constrain the other one, and make it work. With mimetic algorithms, some people have done that. Not very common in this less common. But yeah, it can be done. It's different, of course, if you are solving two different problems, because then perhaps it will be more appropriate to use a parameter and a hyperlink, and we'll go for that. Rather than two different problems. If all you're interested on is refining solutions in specific regions, then you will have. But that would be the difference from my point. Depending on what you're solving, if it's completely different, it's better to solve it. It's the same that refining is maybe different.
If there is two different problems, and if you don't at the center, so you could get some of the first problem and the space for the second one.
In that case, perhaps coevolution will be better. As you mentioned, because it's normally not considered a hybrid,
a good example about global vision and bilateral, like evolution was widely used in construction before the competition compared to global vision to developing competition, oil and gas, but from this point of view, for example, the factory estate compared to bilateral. There are kind of some similarities.
There are things that is not exactly the same because in bi-level there is a very specific dynamic. Whereas in the hyper-realistic it's up to you. You could of course impose the same mechanism, probably by levels, but that's not the way it was designed. So I guess you can do it, but it is much more flexible. The bi-level is really a different type of problem. But yeah, they are related. I see coevolution more closely related to bi-level. Personally.
Yes.
Oh. You're asking a very interesting question. I make a lot of jokes about many objective optimization. It's a very profitable research area. I think even random search can be fed up by objective evolution reality. So it's very funny because now you find papers related to crazy ideas. By sorting each algorithm, the solution with respect to each objective, and I add them up, divided by 5 or whatever. And this is better than energy. Of course, even random is better, right? So anything you do will be better than the known algorithms that operate based on Pareto ranking. So that will keep people busy for a long time. I don't think we are moving in any direction. Most of the research, we are just producing more and more algorithms because we were missing motivation for several years. The benchmarks we have now, some of them are easy to solve, others are very challenging, which means we cannot solve them, so it's not fun, we cannot solve them. And there was nothing in between. And many objectives now provide this. Of course, there are real-world many objective problems that are very interesting, but the work I have seen, they normally use a relatively conventional, sophisticated, and they are able to solve successfully this problem. You can even use traditional algorithms. All you have to do is to increase a lot of populations. It will work. But since it will keep busy emo people for a while, I expect it to last for several years. But I may be wrong. I may be wrong. I remember having a talk with Kalyan in 2001 in Zurich. We had the first emo conference. I asked him, he asked me a similar question, but regarding him. He asked me, for how long you did that emo? And at that time, and he would probably deny that if I tell him this, he said that he expected emo to last about 10 years. And then, it was to go down, and nobody would do emo. And I told him, well, I expect it lasts long enough because I will do emo for the rest of my life. And I'm planning to live more than 10 years for sure. So you never know. Sometimes people think this will go away. I don't think many objectives will go away. Not easy. We find another interesting problem. Everybody will move in that direction. But for like the hybrid approaches, for example, numeric algorithms were around for a few years. Several people were working on that. When many objectives started in 2005, 2004, very strongly in 2006. And at that time, some of us thought this would go away. That's what I thought. Then I realized this is not going away because people keep publishing. It's like indicator-based selection is the same. It's another topic some people believe will go away. I don't think it will go away. It's related to many objectives, but it's a completely different topic. Personally, I believe it should not last too long, but in practice, that won't be the case. I think I will expect at least 5 more years of a lot of research. Then probably it will decay, not because the problem has been solved, but because people found something. That's the only reason why people go to a different. The same happened with particles.
Other questions? Yeah, I think we have a question because software engineering we have a different level of abstraction, like work on the requirements level, design level, code level, they're dependent, etc. So, and when presenting with this hybrid, hybridistic, etc., software engineering maybe want to see more people say multi-level, that you have more than levels like hierarchical, maybe have hierarchical global and local, maybe another within another local search again, or single and difficult. But once you change the design, you can impact your code and your test needs, etc. I know that the research may talk later about multi-testing, other further, but how about maybe trying to extend this dialectic of assembly in terms of different levels rather than
I have seen that in single objective. Multi-objective is not that common. Some people have used, for example, agents. The use of agents to work with different levels. Also, I have seen hierarchical encodings that allow to operate with different levels at the same time. But this is, you use this encoding is very restricted. It can be applied only in general. I think what you are mentioning is more general because it depends really on the whole process of designing software. So, no, in that case, I believe it would be more appropriate to use agents. Perhaps also in a parallel. To do some asynchronous parallel. So that you could have the information available and once you have it, you can use it. So be waiting on the time. You could be doing something, trying to improve some aspects. I'm surprised that I think the generic programming didn't get that farther away into it. Because I was expecting in the early days of the generic programming to get deeper, and this would have a lot of implications for software development. And in the early days there was very interesting work, but now most of the work I have seen is single. I really don't know why, but that would be another. Running different agents so that you can monitor the whole software cycle. It would be an interesting application. I believe, of course, it's possible, but I haven't seen
it. Also, from practice, let's say, point of view, is when we want to apply this other method in practice. So, of course, execution time. And we always get this question. So, what's the trade-off between sacrificing because I believe this argument could take longer time because you're combining different algorithms. So, are there any work for Stargate model?
Yeah, some people have tried to do that. There is a lot of work now on surveys. It's just not that much in height. But for multi-objective evolution, there is a lot on this approximation for using surrogates directly. The problem with surrogates is, in most cases, they limit the applicability because most of these approaches can only work with low few decision layers, more than 10 to 15. The other problem is some of the surrogates are not very widely accepted in some communities. Some people don't like them. So another alternative is parallels. I have seen a lot of GPU-based implementations, which are very fast, and you don't sacrifice the essence of the algorithm. You're not really using truth, but that's speeding up by exploiting this lack of interaction in some parts of the algorithm, exploiting parallels. So this could be an alternative. I haven't seen that much for example parallel hyperlinks, but this is a way of doing it. The same thing you mentioned, I have heard from people in pattern recognition. They are very skeptical about the use of interviews because they say, okay, yeah, they work, but I have to process the image and I have to do it in real time. So the algorithm is of no use. I have heard this thing. And that's not really true because there are, for example, FPGA some evolutionary algorithms, and this can be used in real time. It just, of course, is more complicated. Directly in a circle. So not many people work on that, but if you are really interested in speeding up, there are options, hardware-based options or parallelizations, all these, if it's possible, there are some available. For example, genetic programming has a lot of implementation. There are ways around, but of course, computational cost will always be important. Algorithms in general, not only specific.
Thank you, Professor Pereira. I have slightly different question. I know that in EMO you have well-designed problems and well-defined benchmarks that you can use, while in our software engineering community we have really ambiguous problems and we have a lot of uncertainty, and you have really heterogeneous data sets of data, test cases, etc. So for as researchers, we always find a problem to map between those and test, for example, our applications. Is there like a systematic strategy that maybe can help us map so we can probably look for the best algorithm that we can use?
That's a good question. No, there is no systematic approach to that now. Perhaps an interactive approach to doing human intervention to try to select. But hyperheuristics in a way do that. They try to find out, but to be effective, you need to have a way to measure performance. You cannot assess performance of each particular algorithm because of this mismatch in data and all this, then it would be very hard. You need to have, what you could do is perhaps to try more specific low-level heuristics, more tailored for the specific problem. Design those yourself. Is in an interactive way. To try to learn more about the problem and then figure out how to design a global structure. But the uncertainties we can incorporate, of course, that's not a problem. The problem is the selection itself. In optimization, we always assume the model is there. If there is no model, or the model is poorly understood, then the optimization will not be.
Yeah, and here it's just a follow-up question. That's what we discuss sometimes. That most of the arguments, for example, are testing some existing corpus, like application corpus, but when
they don't work, yeah, I know that.
it's different.
I know, that's the real world.
That's the challenge.
It is very challenging. Of course, you can play some tricks to try to adapt to these poorly known domains. But in general, these algorithms are not designed for that. You shouldn't be surprised that it's difficult, of course. They're not designed for these poorly known domains. They can be adapted. But normally requires a long time to use it. Unfortunately, it is like that. And software design in particular is a very human task. I guess it's very difficult to learn from it in this process. Human intervention is to be there. That's why I think interactive is better, because in interactive, you are asking directly to the user and you are guiding the search based on these questions you ask the user. Sort of be more intuitive.
So it is now going to thank our speaker again. So the coffee break will be the next room, then we come back at 11 a.m. So we have our 15 minutes of wisdom about the new paradigm evolution. So see you later. As a programmer, you just receive we will be just at the class level. Yes, try to answer the exercises. But the feedback that we want to see implementation at the mid program, at the time level, at the class level. So when you present this or hybrid as well, say, okay, let's do maybe the classes. And then also take now at these classes and look for the functions. Because the search space would be lower than we can work in our classes to expect over time. The good thing is something, we have a lot of open source. So for open source software, source code is available, but reports are available, access to it, they are open source. Yes, because everything already so, yeah, so that would be different. And also for this particular project, we have data from collaboration in industry, so based on that was my suggestion. You are really thinking to use between programmers and trying to solve the bug. That's another source of data. So, yeah, that's yes, it's all so I would say we're just extend the basic program. I will tell you what we did the way so yeah,
We have EPA, but the paper
That's fine.
The question is how do you adapt it?
Yeah, so that's as far as like a high development, each of the information happens. Start from biology.
You need to study. You should move that.
哦，你找这种吗？还有富裕的。啥玩意儿？你可以跟那个前台用。没事。我去，要给我选装的。我在万水，在放假了。我这个在就是意思我10月底就是想把这个当做因为它好多地方像体验分析我如果能完成的话，月底对。我觉得早点完成好。那天晚上那个完了，我当时就我建议给他。最高就是。
아, 병원에 선생님이 쉽게 빼면 그러면
一般都是这样。就每个人其实每个人。我就不知道你们那个他觉得你在 Facebook 上面那个播客会分享，然后你在 Facebook 上达到了录像都是一段段推荐啊，你是方面
저 제가 다섯 개를 어때서 새로 생성된 나도 자고 일어나서 집에 하니까 다시 그래서 지금 두 개 만드는
하나 만들면 새로 만들면 두 개를 두 개로 쓰고 새로 만들면准备给多少个人能看到链接？하나 만들 때마다 지금 다 만드는 거만
네, 만들어지고 나서 제일 지난해 서브스크립션 안 나오고
管理员他会일단 세정물 되면 저번 것도 거기서 조금 돌린 사람이 있나 보죠.
네, 칼을 하고 이제 친구도 거기서 3일이 지나면 스폰서십을 생성하면 3일 뒤에
完了，我就说一发，他当时在实验室发了一个，发了，给网站的家长发了个图，就是实验到这个实验室的那个效果，太让人逗了。对，就在这边。
Is this a longest primary class? I wasn't sure.
到那个场合是必备的，必备的。可以的。完了之后，我还想着要说菜。去吧，我也不可能。
제일 좋은 건 승부욕이 시험. 그게 테스트 데이터에서 이제
쌤이랑 테스트가 같은 데서 나온 거죠. 똑같이 와.
네.
사실 예를 들어서 트레이닝 전체 셋이 S가 있어 중에 트레이닝 테스트 데이터 세트가 어떤 말씀이죠? R에 대해서 어떤 학생은 F라는 함수만 좀 성취하시고 F라는 함수는 아르제에서는 스퀘어 그걸로 했을 때 G보다 더 좋게 나왔지만 나중에 테스트 데이터셋을 했을 때 G가 더 좋게 나왔어요. 그냥 어차피 그러니까 알고리즘이 많은 거라서 네, 그런 건데 나중에 이제 갑자기 그런
트레이닝에 너무 잘했는데 테스트에 대해서 오히려 안 좋다.
아
I haven't divorced yet. I get it. This is going for the yeah, it's
마이너 경우에 중에서
Like difference.
So I'm going to load some stuff in the car back to school at 4:30. I can't give you the lift back over because.
Oh, okay.
So if you could overall drive for 30 minutes, I'll ask you. I'll have Frederick. I'll have Frederick.
So thanks for attending this session. So now we have our third keynote speaker. And we have an insight from the multitasking flourishing computation, which is a new part in the area of computational intelligence. Yu Sun is currently a full professor of computer science in the School of Computer Science and Engineering at the Nanyang Technological University here in Singapore. He served as the director of the Computational Intelligence Research Center from 2008 until 2015, and he's currently director of the A-Star C-Technically Dome Lab of Complex Systems. He's also the PI of the Data Analytics and the Complex System Program in the US West Corporate Laboratory. And this is $75 million project. And you'll see that he's also in mathematics at the University of Scotland in the UK. His research focus is computational intelligence, machine learning, and so on. Founded the Transport and under the SSBSE Computational Intelligence Society, and served as the chair from 2007 to 2010. In 2009, worked with the founder of the Computer Journal and the student president of the Institute of Computing and then he works on numeric computation and related area. He received important team at the Computational Intelligence Foundation of Summer Award and the 2012 at the International Computation as well. Also, he's very familiar with computation. He's the co-founder of the for the Spring of the Series on studying machine learning and optimization and computation with the learning from application testing. He's also computational application testing, neural networks and learning, application and application testing. He's also the founder of the Institute of application testing and learning computational ability. And he has a different pattern for so yes, that's of course
Sorry for making it so long. By the way, if I doze off, please let me know because it's PM at night in Singapore right now. So I should be sleeping. So before I go into the talk of towards smarter optimization and everything multitasking, just like to show a few things about the school, the university, and Singapore. So anyone in Singapore? Great, so we have quite a number of you. Do come over again. For those who have not, let me just give you a brief introduction of Singapore. Small, not too big, just 25 kilometers by 48. So if you look at the small little island there, this one, this is Singapore. If you were to zoom in, it's not working, but it's okay. So if you look at the small island, if you look at the green dot over there, that's where NTU is. Airport. The airport is on the right. So if you visit me NTU, you have been through the entire Singapore. That's just how big and how small we are. So these are the two collections, the two buildings of Singapore. The one on the upper right is the art design museum. The one on the lower portion, that's what we call the Hive. That's our latest collection. NTU spent $1.2 billion last year just on building alone. How is NTU doing? In terms of ranking, for the last 3 years, under 50, let's just say. Overall, we're ranked as 13. Funding. In terms of citation, guess which is the curve? We are increasing exponentially. Not in terms of initial citation, we can index. How about the school? 121 Master of Science Engineering students, 262 PhD students, and 71 faculty members. So currently I'm wearing various hats. I'm chair of the school, computer science engineering, director of a complex, director of a data science and AI research lab, and also I lead the data science and complex system with Rolls-Royce. Tell you more about the Rolls-Royce project later on. Speaking of the school, I'd like to share this joke. This National Taiwan University. What is the initial of National Taiwan University? Aviation. NTU actually. Probably they make a mistake. Use themselves as first. And Bengali University is also ranked as 1. The US News and World Report in 2015 was ranked 7. In terms of the citation, under the Microsoft Academic Search, we are ranked as 2nd, right after Microsoft. Obviously, Microsoft must have done something in that search. Okay, so just to give a few showcase of the projects we have in Singapore. So at the moment, for example, we have this project with Rolls-Royce, lab at NTU funded by National Research Foundation. That's our key funder. So this is a 75 million project for 5 years, with 20 million devoted to data analytics. So the key slogan we use is that data as the new fuel. Some say data as the new oil, with the raw material they use to mine. Some say data as a new currency. So personally, my interest is in the area of design, where lots of data are produced during the design process. Data. And to try to improve the search process, in particular for myself. As I mentioned, there's also the Data Science and AI Research Center. This is initially seeded by the university with 8 million. I think with the 8 million, usually they expected 7 times return. million. So that's what I'm supposed to bring in later on. On data science and AI, right now data science and AI is really hot in Singapore, throughout the world as well. We also have this 11 million funding from the National Research Foundation. So this focus on very high TRL, very high translation research. So basically the government wants to pass the project over to us whenever the agency has any work to be done. The area of basically video analytics and wireless network. So one of them, for example, smart surveillance. So this was just awarded recently. We also have cybersecurity. This is something that's picking up with only about 1.5 million from Boeing, not Boeing, sorry, British Aerospace. BAE. We have a project with Tool Create. This has begun about 5 years ago. So the first phase has ended. This is the area of this smart mobility, focusing on, for example, electric cars, autonomous vehicles, for example. And currently we just renewed the project with another 40 million. So we have actually professors coming from TUM that stay with us. There's also a project with BMW. Although the money is just a couple of million, not too much. One on active learning, for active living for the elderly, 26 million. And one on games, 34 million. So why am I showing you this? I'll let you know later on. So on the average in 2014, our average faculty grant is about 1 million, 1.1 million. So every one of our faculty has about 1.1 million funding. Is that a lot? No. Why am I showing you this? Because as the chair of the school, I still have 10 positions to fill. From assistant professor to associate professor to full professor. So we have, for example, in the area of machine learning and data analytics to be filled. It can be 1, it can be 2, it can be 3. If I need more, I just have to go to my provost, ask for more. Can't fill up the 10 I currently have. We are interested also in high performance and custom computing systems. Very much I'm interested in the neuromorphic chips, for example. Computer security. This is the area that's most relevant to all of you, I think. All of my people in this area are from software engineering. They are currently holding quite a lot of grant from this. But all of them are from software engineering. AI, artificial intelligence, intelligent agents and optimization is one of them. Okay, so these are some of the important slides that I hope you remember. Okay, back to the talk. So in this talk, I'll basically focus on first. What do I mean by that? I'll show you later. And I'll draw some points for what Carlos had mentioned. Introduce it to you just now. And I'll then move on to something called multifactorial optimization or application multitasking. Something that's pretty new. So this is the outline of the talk. So what's happening today? That's what Carlos has mentioned. We have evolution algorithms, genetic algorithms, genetic programming, and so on. We have swarm algorithms. We have all different names: BERT algorithms, full search, E algorithms. You can think of any animals. I mean, you can find an algorithm out there. You have the classical method, mathematical programming. This is something nobody complains. You have a hybridization of them. So you have a combinatorial effect. So it becomes empty hard problem by itself, just to choose which algorithm to use. So what's happening? Algorithms. Now the question is, why do we re-optimize all the time? Can we have something that learns across problems? That's what you have in machine learning. They learn, right, from data. Can we learn from different problems and search faster in the future? But if you notice, current optimization solvers always start from scratch and assume a ground zero knowledge state. For example, you solve a problem, given a new problem, you start from scratch. You don't make use of the knowledge from the previous problem. So as a result, our capabilities do not grow. It does not evolve with the problem solved. But humans doesn't do that. We solve a problem. The next time we solve the problem again, they're smarter. Isn't that the case? Let me give you an example. As a baby, we learn to flip. That flipping knowledge, we optimize. At every stage, you optimize. That flipping knowledge will be useful for learning to crawl. And while we are crawling, we optimize. We do optimize every time. Pass through the ability to walk, and then subsequently to run. So you optimize at different stage and you pass it across to the subsequent, supposedly more complicated problem. Same, you ride a push cart, and then you ride a tricycle. That knowledge of balancing is useful for riding a bicycle, and subsequently maybe you ride a bike, a motorbike. So these are examples where we optimize at different stages, and that knowledge is caused to the next problem. For example, in a swarm robot controller problem, although I'm trying to work on two different problems, obviously the knowledge in the two different problems are useful to each other. So can I then use knowledge for one problem or solving it to help in the next problem? Or can I solve them together? So I'm going to show you examples for that. And I will particularly draw examples for aerodynamic design because I work in the field for more than 1.5 decades. So aerodynamic design, be whether you optimize F1 car versus you optimize the wind lift force of a plane. They are both aerodynamic problems, fluid dynamics problems. Can knowledge for one problem be used for the other? Similarly, graph, this is a routing problem. Usually they're represented as graph. Graph has structures. Can that structures be obtained from it such that you can use it in the future? So these are some examples that I'll talk about. So as such, I'm going to talk about this smarter optimization. In particular, I'll use machine learning methods to try to extract explicit knowledge from problems and transfer it across to other problems in future optimization. Let me show you one example. So this is a field which Carlos had mentioned. It focuses on solving computational expensive problems. So why is this computational expensive? Because they involve either finite element simulation, fluid dynamic simulation, or even electromagnetic simulation. So as a result, every one of these runs will take 1 hour. So I have a problem with Honda that one simulation takes 1 night. So imagine how long it will take to run 10,000 function evaluations. And it's very common For evolution optimization, we use up 10,000 function evaluation. Imagine 1 hour will take you 1.16 years. You do 10,000 lines. I mean, just 10,000 evaluations, not 10,000 lines. So in this field, this is what was mentioned previously. It's known as surrogate system in the algorithm, for example. So the key idea is that you still solve the nonlinear programming problem, where you have function f of x. It could be a multi-objective problem or single objective. Nonlinear function g and some real parameters. The fact is that the function itself is expensive to compute, or it could be the constraint that is expensive to compute. So the key idea we use surrogate. Why the term surrogate? Remember the heard of surrogate model? So instead of the original function, you use another function, and that function is usually a regression model. It could be a classification model as well. That we use the data that are produced along the search and create a model out of it. And instead of using the original model, you use the surrogate model. Or rather, you use the meta model or the approximation model as a surrogate. So in the mathematical programming field, there's actually a guarantee that in the exact model, let's say the original function, with the approximation model, you can guarantee conversion to the true optima of the original model. So there is a guarantee proof available. In the context of mathematical programming, there is local optimization. So the many algorithms combine evolution algorithms with local optimization. So the fact of doing that means that you have a guarantee of at least local optimality. So that's the advantage of numeric algorithms in the sense that you will never do anything poorer than mathematical programming. So people will not criticize in a way because of lack of proof of conversion. So the nice thing of using meta models or surrogate models is that these are often statistical models. So you have some insight to the model itself, to the parameters, to the effect of the parameters, even having some idea about the constraints, the non-linearity of the constraint, for example. You can understand it from the model itself. Okay. So some of these problems that are tackled before includes like this, for example. I work with physicists and chemists. Not this one. I'll show you the other one later. This one is a cantilever structure. It's basically just an irregular structure rather than a regular one. So I'll show you this later in the next slide. So I work with British Aerospace, for example, on optimizing a plane form. Rolls-Royce with optimizing the turbine blade. Honda with optimizing the rear. So as I mentioned, all this involve a lot of simulation, especially fluid dynamic simulation. So we try to introduce algorithms that basically when you switch between an original function and the surrogate model, we converge to some good solution fast. So the key idea is that we don't run, in fact, all the way to converge and global optimum, because in real world problems, nobody knows where is the global optimum. They are pretty happy as long as you can do something better than what they have. And in combinatorial search, for example, as long as you can give them a feasible solution, they are quite happy. Because it's so difficult to just find a feasible solution. For example, early works was like in 2003 in aerodynamics journal. So for example, for this problem, with Honda problem, this is a GA design. Design differs from that of us of using, for example, CMA, yes, everything strategy, and differs from our algorithms that uses surrogate, for example. So we shown that we could reduce the computational effort by 50%, which is quite significant considering that, for example, this problem, I think it's one evaluation is about an hour. use this because otherwise it can't publish. The actual problem they have is one month, 1 day or 1 month. So it's impossible to publish. This one. So as mentioned, I work with physicists and chemists. So the key idea is to find the global optimum of all these molecular structures. In this case, it's H2O water. I was told by my chemist colleague that if you can find anything more than 20 water, the global optimum of 20 water, you can publish a physics paper. Because they still don't know where is the global optimum. So it's a okay problem. Basically, you try to change the distance between all the atoms to find the best structures that gives you that's the most stable, so to speak. But this is a problem where, unlike normal global continuous optimization, every possible solution is a solution. In this case, there are basically it has to be a stable state. The only thing that really exists is either local optimum or global optimum. There's no any other solution because it has to converge to something that's stable. Something that is not stable cannot exist in real life. So this can also be applied, for example, to material design. So why did I bring up this problem? So I mentioned about explicitly transferring between models. In the context of multi-objective, for example, what we did is that, imagine I have two objectives, and it happened that one objective is more expensive to compute than the other. So I have two objectives, for example, one being stress, right? The other one being drag friction, fluid dynamics. So you notice that drag is much more expensive to compute compared to stress. Because one of it involves a very expensive simulation, the other one doesn't. You have two different functions, one is faster, one is slower. So the key idea is how can we then make use of data from the one that is faster to augment data that's one that is slower, such that the prediction on the one that's slower could be higher. So in this manner, you can speed up the entire optimization process. So we explicitly obtain the data from one objective versus the other. So where are all these data derived from? Population-based search, one of the nice things is that it creates samples along the search. So the data actually obtained from the population itself. So as you search for more and more generation, you get more and more data. So these are the sample data that we use. So this is one example of explicitly performing a knowledge transfer between objectives, for example. In another case, for example, I have a project in the area of large-scale engineering simulation for complex statistics system in the area of multi-agents, for example. In this particular case, we developed a system that's for supply chain management system. So it's one that allows you to model the problem, supply chain problem. And then after that, you can perform simulation. This is something that your field should be very good in, like developing this kind of system. And then subsequently, doing optimization inside. So along the way, you do what-if analysis. And we have analytics tool inside to analyze the results, for example. So this led to a few, it was licensed to a few companies and led to a startup. So in this example, why am I showing this is because of the routing problem. One of the particular problems inside is routing. And as I mentioned previously, in routing problems, very often we define them or we represent them as graphs. As structures. So if we could, in a way, identify the structures, that means under what kind of structures it led to a particular optimal solution. And if you can identify this kind of structures, over time, when you solve new problems, you can solve it faster. So the key idea is understanding the structures. It could be substructures, it could be the whole structures as one, which include the cost. So I'm showing you here two different problems. One is a CDRT problem, one is a capacitated bigger routing problem. This is a capacitated up routing problem. This is on the nodes. This is on the up. If I'm not wrong, when you do branch testing, you have something similar. Like software engineering branch testing. I read some papers on that. I'm not an expert in software engineering, by the way. So I'm here to learn from you on software engineering. I helped to teach software engineering before, so I'm not an expert. Good enough for the undergrad student. So the key idea is, for example, so Carlo was saying about pneumatic algorithms. One of the things about the field of pneumatic algorithms is interested in what I call pneumatic computing field of pneumatic algorithms. When Dawkins first defined NIM, he actually defined NIM as a unit of information that resides in the brain. He calls it as a replicator in human culture evolution. So if you look at it, oh, by the way, since now I mentioned the word NIM, does anybody know how the word NIM comes about? And why is it pronounced as NIM, not NIM? Many of us will probably call NIM when we saw the word, right? I'll tell you the story. So basically, Dawkins was looking for a word that is similar to the word memory. Oh no, sorry, imitation, to imitate. Memory comes later. So to imitate, he found the word mime. M-I-M-E-M-E. That is Latin, I think. Latin for to imitate. But I find that it's two syllables. He doesn't like it. He wanted something monosyllable. And rhymes like these. So he found this word memory. In French, it's written as, any French here? Is it written as me?
Memoir.
Oh, something like that. So that's how the word me came about. It was written in his book, Self-Esteem, in chapter 11. So that's how meme comes about. So, in other words, he wanted something that is similar to genes. Genes is what is gene? The instruction for protein synthesis. In fact, if you look at Susan Blackmore's book is called the Meme Machine. He defined memes as an instruction for building artifacts, creating artifacts, or for creating behavior. So it's very much a compact representation like genes, human culture evolution. But somehow the definition of memes has been defined in pneumatic algorithm instead. So personally, I'm very interested in bringing back the original definition of meme, which in this case, I define meme as a matrix. In this example, for this routing problem. For example, if this is a routing problem, this is a task distribution. Each node represents, for example, you need to send your vehicle to travel to every node once to collect some package or to deliver some package. So it's represented as a graph. In this case, I have 4 vehicles. So that's why you see 4 different classes. So the question is, using some optimization algorithms or evolution algorithms, I can obtain this solution. So if this is the optimized solution, this is the initial problem. Can I find some form of matrix? It's just a linear transformation. Okay, it's a rotation and a scaling. I have 4 different vehicles. Usually what people do, they'll cluster them into 4 different clusters. So in order to arrive at this optimized solution, how do I identify a transformation matrix that will scale and rotate some of these nodes in a way that For example, these three nodes are nearer to each other that they get clustered. And that three nodes from here, they are scaled and rotate in such a way that they will come closer and get clustered. So how do I then basically find a matrix that will make it converge to this solution, so to speak? So that in the future, given the new problem, I can search my society on memes. So that society of memes is basically a collection of matrices, collection of previous problems that has been solved. So that given the new problem, I will find a very similar matrix or a generalization of those matrices. It could be a combination of different matrices. Such that given a new problem, I will make the transformation such that I am not at the global optimum, but near to somewhere of the global optimum. Such that from there, when I do search, it will be faster. Learning plays a part by learning from past problem solved. Apply on some of these classical problems. These are not our benchmarks. These are benchmarks that are more than, I would say, most of us, older than most of us. So this is, as I mentioned, consider the visual routing problem, the ARP problem, arc routing problem. You can see that by learning from past problems, I can achieve significant speed up. So what I did is, given a set of benchmarks, I solved part of it, and given a new problem, I look at the previous matrices that I've archived so far. And from there, I make an initial guess, an intelligent guess of what a global optimum might be, and then I search from there. And as a result, I can speed up the search significantly. This is somehow similar to how people solve problems, we humans solve problems. Given a new problem, we will never start from scratch. We will use our prior knowledge, make a what we call intelligent guess, and solve from there, so to speak. And this is also very much motivated from the field of transfer learning in machine learning. So we try to make use of data that are similar to augment new problems where data is limited, so that we can speed up the search itself. So this is one example. So I hope you have roughly understand market optimization by explicitly using machine learning methods to try to derive knowledge from previous problem solved and hence speed up future problems. Now, we use quite sophisticated machine learning methods to try to understand the data and try to transfer the knowledge. I'm going to show you something much simpler. You know, the nice thing about evolutionary computation is its simplicity. That's why we have many people that use it. So the question is something that we have done recently known as evolutionary multitasking. So I'm particularly intrigued by my boy being able to watch the TV at the same time, play an iPad at the same time, drink the tea at the same time, eating his TVs at the same time. They're amazing. I don't know whether it's a good thing or a bad thing. Our kids, our new generation can never stop doing something. They have to be doing something, or multiple things at the same time. So I was thinking, if they can do so many things so well, can we design a machine to multitask? You know, we have that. We have machines that multitask. Parallel computing is multitasking. Not so much. We don't really solve them using knowledge from each other, each task. We treat them as independent processes in parallel computing. But humans will do that. We will make use of knowledge from different tasks. We'll make use of knowledge from all different tasks that we've solved so far. So as a result, this area is born, so to speak. So I was wondering, can we solve multiple problems at the same time and get faster? So I look into some areas of neuroscience in the aspects of whether humans can multitask. And interestingly, neuroscientists say humans cannot multitask. We are very bad in multitasking. In fact, there's a lot of switching costs. That's why we get tired so easily. Every time we switch from one task to the next task, we get tired. This is what we call the switching cost. But machines do not get tired. So can we get machines to do that for us? So this is, so there's several works published in the recent years. In fact, it was only in 2000. In fact, it's not even published. Yeah, oh, I think this one is probably online. So it's this one. I'm not too sure about algorithms on cybernetics. So we have one on single objective, or rather multitask, single objective. More higher level perspective, it's much easier to read. More on the level of cognitive multitasking. Or multi-objective, multifactorial. So multi-objective, multifactorial, you have multifactorial single objective. Now, consider this. I have a situation where I have k optimization tasks to be performed. I task, each of these I tasks has an objective function to be minimized, in this case. One of the strengths of evolution algorithm is implicit parallelism, and that's what multi-objective optimization uses as well. Multi-objective evolutionary optimization uses as well. So I'm going back to fundamentals and see whether I can make use of this implicit parallelism to achieve evolutionary multitasking. And over here, instead of calling it implicit parallelism, I prefer the term genetic transfer. Basically, from the perspective of a transfer of knowledge. Because there is knowledge that transferred between tasks, for example, during the search. So the key idea is, how can I then solve multiple tasks together, given that each of the tasks has a function? So each task represents a problem. So what's the benefit? One of the examples of this benefit is that a simple task complement each other in solving a more complex one. Let me give you an example. Many times you are given a very complicated problem. What's the first thing you do? You try to solve it by divide and conquer, right? You remember something that you have done, a very simple one, and you try to solve it that way, and it helps you solve. Let me give you another example. If you want to study aerodynamics, one of the things that you need to know is PDE, partial differential equation. Knowledge of PDEs, it will help you solve this learning problem of aerodynamics problem. Without that knowledge, that piece missing, you're taking a lot more time in order to understand aerodynamic theory. So that's one of the key motivations. And the sharing of knowledge, in this case, in the form of encoded genetic material, because in evolutionary computation, you have this encoding of genes in the compound. Is this sharing of this genetic material across different problems, that along the way you see that it is possible to get free lunch from solving different tasks. That's to say, when you are solving a particular task, that particular set of genes is also, or subset of genes is useful in the other task. And you get free lunch as a result. And I'll show you that I could actually search faster by solving two tasks sometimes, as opposed to one independently. Let me break this down into three cases. Three cases, multitasking can work. The most obvious case is that I have two different problems with complete overlaps of input variables. I have a research fellow who is interested in software engineering, and he applied this to software engineering hobby. And the paper was accepted at SSBSE 2016. So I'm still trying to figure out that software engineering problem. So, but I can pass you the paper. According to him, in software engineering, when you all do branch testing, there's this thing called two-step branch testing. You'll choose a branch, and then you search on this branch thoroughly to find it's basically a maximum coverage model. So he was telling me that many of these branch has this overlaps in the parameter. And as a result, you can solve them together. Such that knowledge, or rather genes that are useful in a particular branch will be useful for the other. And you lead to quite significant speed up. I won't go into the details of that application. I'll show you some synthetic problems. Case which is complete overlap. Again, I'll show you something that I'm familiar with, aerodynamic swing design. So having worked with aerodynamic swing design, for example, if I'm trying to optimize this wind plane form, or airfoil in this case, for each of these airfoil, the only difference is the Mach number. That's to say, the speed that the plane is flying at, is operating at. For different Mach number, you have different optimal design. So for the same wing, your design variables are exactly the same. Right? The only thing that differs is the operating condition. In this case, it's the Mach number. So if I'm trying to solve what is the best design for this 1, 2, 3, 4, 5 different airfoils, I can solve all the 5 of them together, such that, again, knowledge for one can be transferred to the other. So this is a case of a complete overlap of the design variable. On the other hand, I could have a problem, a black box problem, with multiple strategies to try out to see which is the better strategy. So the black box problem is the same, it's just the strategy being different. I can solve all of them together because of complete overlap of the design variable of the black box. Let me go to the second one, which is partial overlap. Again, let me use the example of airfoil. In this case, I have 24 parameters for this airfoil structure. I could be using one that is 22 parameters. Nobody knows which is the best. It all depends on the resolution. The higher number of parameters, the bigger the search space, the more expensive it is. Or I could use one that is just 12 parameters. Bear in mind that 12 parameters problem has 12 parameters overlap with a 24 parameter problem. And the 22 parameter problem has 22 parameters overlap with 24. So again, there is this overlap in the parameters. Together, what is being searched upon will be useful for the other problem. Similarly, for routing problem, again, if I represent it as a graph, if halfway through, one of the customers say that I won't be around, don't bother to deliver the package. You know, there's only a minute difference in the graph. But very often you will see that we re-optimize. So can you dare and solve them together? You just move along in the search and see if you can converge faster. Let me show you another more interesting case. In a case where there's no overlap in the parameters. For example, I know many of you in software engineering work in the area of service computing. In service computing or in cloud computing, you have this thing where multiple solvers exist in the cloud. You have multiple jobs sent to a central node or central point to be serviced. Imagine the situation where you can solve this different problem faster because you make use of the knowledge from the different problems, even though they could be different. I'll show you some results later on that even when the problems are different, it is transfer. So this is one that would be very interesting in the context of cloud computing. So imagine that you can make money by people sending jobs to you because you learn to use the knowledge from the different problems. So before I move on, are there any questions? Yeah.
So what about overlaps in genotype space? Is that
Going to do the overlap will be in the genotype space. The only difference lies in the phenotype space. So I'll show you a representation that's pretty commonly used in the context of combinatorial space. So before I move to that, this optimization problem. So we call it a multifactorial optimization for the context of multitasking. So I want to find the optimum design or the optimal solution for F1 to Fk tasks. It could be 2 tasks, it could be 3, it could be 4. I've not tried anything more than 10 so far. So each F represents a factor, hence the term multifactorial. And the term multifactorial is also derived from biological background. So we refer this as a k factorial problem. Now I want to define 3 things. For every individual P in a population, so individual Pi, I have factorial rank, which is a rank of that individual on a particular task K, relative to all other individuals in P. So if I have 3 tasks, you either be rank 1, 2, or 3. Okay? Scalar fitness is then based on its best rank over all tasks. How good is this particular individual across all the tasks? If it's evaluated on all the tasks. Okay? So if the individual is very good on task 1, so you'll be ranked 1. So its fitness will be 1 divided by 1 is 1. Scalar fitness will be 1. That's the best you can get. Skill factor of the individual is the one task among all other tasks which is associated. And here we associate it with the task that it performs best. So in this case, the one with the best rank. That is the skill factor. It means if somebody asks you what is your skill, it must be something you're very good in. Okay? So that's the skill factor. So the algorithm is pretty simple. It's just a variant. Just like the NSGA multi-objective algorithm, they are all variants of the original kinetic algorithm. This is also a very simple variant. The key thing lies in a unified representation. How do you have a representation that unifies different problems? So I'll talk about the unified representation later on. And then you have your initial population, where usually we randomly create it, and we assign it with some key factor, some skill factor, which could be randomly assigned at the moment. I mean, imagine that all of us, right at the start, we don't know each other, we don't know what this problem is about. We will have a random skill factor, right? Until proven otherwise. You evaluate the population for skill factor, and then you create offspring based on associative crossover or mutation. You assign some skill factor to the offspring itself, and then you evaluate with a particular skill factor. In this case, you can choose to use local search or not, depending on whether you want to use the genetic algorithm. And you just combine the parent and the child to create a new population. So it's pretty simple. It's just additional stage. They focus on associative crossover mutation and then the skill factor. And I want to repeat that this unified representation is the key thing. The genome type is the key thing. So as I mentioned, the most important ingredient I would say will be a common representation. So I'm going to show you one that's commonly used. So here, imagine I have a problem I have a task that's 12 dimensions and another task that's 8 dimensions. Bear in mind, I don't do 12 plus 8 to become 20. That will increase the search space exponentially. Okay? So what we do is we find a dimension that is equal to the maximum of the 2 problems, for example, or 3 problems. For example, I have a 1 problem with 12 dimensions, 1 with 8, 1 with 20. The maximum of the 3 will be 20. So I'll choose a dimensionality which is the largest of all the problems. And here we use something known as random key representation. Zero to 1. Combinatorial problem. One is a task one is a right. So I have a chromosome that is 12 dimensions, and I use decode. So this is the given type representation. During the decoding, for the next set representation, for example, I use a binary decoding. So it's 12 variables. I use all the 12 variables I decoded. Basically, this is a very simple example. Anything larger than 0.5, it becomes 1. Okay. Now, for the 6-dimension Kelvin-Sysman problem, I just take the first 6 dimensions. Why the first 6? Because this is a very new area. I haven't looked into adaptive aspects. I'll leave that to the future. So my students say, oh yeah, we can have something that is evolving along the way, but let's keep it simple for the time being. Just the first 6. By doing this, what happens? I'm forcing the 2 problems to have genetic overlaps. So the first problem, I will decode all the 12 parameters. The second problem, I have a decoding on the first 6 parameters. By doing this, whenever I do a crossover and mutation, both problems are involved together in the first 6 parameters. And if it happens that this first 6 parameter is good for task 2 and happen to be good for task 1, I'll show you some results of when it works, when it doesn't. Look at it. It is quite similarly how multi-objective works. It's just that multi-objective, they look for diversity of solutions for the different objectives. But in this case, over here we are focusing on the weights that we focus from the multi-objective perspective. The weights that we focus on is different. I'll show you some similarity and differences with it. The multi-objective later on. Now, when you have crossover, we have 2 problems. We go to a unified space. So the key idea again lies in the unified space. Bear in mind that here I'm using a very, very generic one, which is based on random representation. You can always use some representation that's more specialized, but yet suitable for different problems in your domain. Because if you look at even the scheduling problem domain, we don't even solve different problems together, even though they could have their own representation. So in this case, if I have unified space, crossover, and allow the genetics or the genes to be transferred between the same task and at the same time between the different tasks. So you have this form of what we call implicit genetic transfer. And I mentioned something known as associative making. All you simply say is that the probability of chromosomes making with each other crossover is higher for those that share the same skill factor. Prefer to mate with a teacher. An engineer would prefer to marry an engineer. So the elitists will tend to want to marry the elitists. The elitism is to promote elitism, in fact. Let's promote convergence. When you have a teacher and an engineer, you are focusing on diversity. Less convergence. And basically, the offspring simply will inherit the skill factor of his parents when he's created. Just like how we learn from our parents, we imitate. You know, when the parents cross over, you lead to a new child. Now, what is the skill factor of the child? You do inheritance from the parents. If the parents have two different skill factors, then you choose one with a probability. Now, this is something that Carlos would like. Distinction between multitasking and multi-objective. So I want to say that both multi-objective and multitasking focuses and make use of the implicit parallelism of evolutionary computing, simply based on sampling of the population. Whereas evolutionary multitasking uses implicit parallelism to exploit the complementaries between distinct tasks. So it tries to promote this gene transfer between tasks. Whereas multi-objective focuses on competing objectives. Focus on conflict. If they don't conflict, you don't want to use evolutionary multi-objective because they'll be agreeing and they'll have the same optima. So they focus on different things. In particular, if you look at this Pareto front. So in EMO, multi-objective, your preferred solution says P2, P3, P4, and P5, which is 1. But for the case of multifactorial, you're only interested in P2 and P5 because you want the global optima of both tasks. You're not interested in the competing aspects of it. Unless you are focusing on multitasking, multi-objective. That's a different thing. Here I'm talking just in terms of multitasking. So I have 2 different tasks or 3 different tasks. I just want to find the global optima of the different tasks, but at the same time. So by making use of this, complementaries between them, and I search faster. That's the idea. Now, does it work? Let me give you a very simple example. This is very intuitive. So I have 2 functions over here in continuous, for example. It's easier to use continuous functions to illustrate because you can understand the continuity aspect. In combinatorial problem, it is amazingly complex because just the definition of neighborhood is a pain because it depends on the metrics you use. What do you mean by neighborhood? So that's why I'm using the context of continuous function. A restricting function in this case is a very, very multimodal function. So this is a 2-dimensional function. The y-axis is the objective fitness value. So I'm drawing this 1-dimensional representation. So the red curve represents restricting. Now the other curve is a blue one, which is a sphere. In this very simple example, when I solve these 2 problems together, simply because I'm lucky that this is a nice smooth envelope of the very multimodal problem. and they happen to have the same global optima. Obviously, when I solve the two together, the knowledge of solving the blue curve easily helps me to converge to the global optima of the red curve. Right? This is very, very much intuitive, no brainer. So as a result, when I solve these two problems together, I lead to very much speed up in solving the multi-model function. So you could say this is just pure coincidence. So if I were to shift it a little bit, such that the global optima of the multi-model function differs from the local to that of the simple function. I shift it a bit. As you can see, I'm still getting a lot of speed up. So what does this show? This is showing that I'm solving two problems at the same time. This dotted curve shows that I'm solving two problems at the same time. This shows that I'm solving only the multi-model problem independently. Okay? Now, what if I move to more complicated problems? So I have two multi-model problems. In this case, again, both of them have the same global optima. I solve them together. You can see that both are helping each other, such that MFO, in this case, this is better than solving it independently. This is also better than solving it independently. You could say that because they share the same global optima. But if I shift it again, just to ensure that they do not have the same global optima, you can see that by solving the two of them together, I'm still getting speed up. Due to the complementary between the two, such that when I'm solving one, get subset of genes that has been, which is useful for one problem, happen to be useful for the other problem, in guiding it towards the global optima. Okay? Now, what if I were to move into cross domain? Previously, it was just functions, continuous functions. In this case, I choose three problems. One is a quadratic assignment problem, okay, which has a totally different search space from a knapsack problem, which has a totally different search space from a continuous problem. You see that by solving the three tasks together, I led to speed up compared to solving one of the problems. So the dotted line represents single object, represents single task, represents the multitasking. You can see that they are all better than the original. And note that I'm plotting them based on per problem. So to speak, if I were to add up the time to solve each of these problems, it will be much longer compared to solving three of them together. So I'm drawing at a scale which is disadvantage to multitasking. Okay. Now, the reason why I'm showing this slide is because I want to show you, like machine learning, where they have positive transfer, they have negative transfer. I'm showing you a case where negative transfer can occur, so to speak. Again, the single tasks are the dotted line, so this multitasking is better. This single line, this single task, multitasking is better. But for this problem, single tasking is better than multitasking. I'm being unfair because I'm drawing them based on the same time scale, but I'm actually solving three of them together. So if I would add all three problems sequentially, you'll actually take more time. But still, I just want to show that there is negative transfer. Let me give you an example where negative transfer will occur. Imagine that you are learning aerodynamics and you think that learning geography will help. Do you think that's possible? Not possible. So negative transfer obviously occurs. So the key thing is, how do you know when you have positive transfer and when you don't? But how do you know when? Let me ask the question back. I often ask people, how do you know two objectives are conflicting? But people still use multi-objective. Anyway, that's not the point. The thing is that, yes, there can be positive transfer and there can be negative transfer. So the key research is, how do you know when you have positive transfer? So the key study will be over there. Similar to the context of machine learning, where we look at positive transfer learning and negative transfer learning. How do you mitigate negative transfer learning? Okay. So we have also applied multitasking to multi-objective. So we have, so to speak, multitasking, multi-objective. We applied to a real problem. So these are NSBA problems. I won't go into the details because the algorithm is quite similar. As I mentioned, it's just a variant of it, of the original genetic algorithm. You are free to change the operators, be it differential evolution, be it particle swarm, or whatsoever. The key idea is, like what I say, lies in the representations and then the subsequent and skill factors. Just the key points. So, key thing is, we've shown that we've gotten speed up in the context of multitasking, multi-objective as well. And we applied to a composite manufacturing problem. And as usual, in any papers, we'll just show you good results. So I won't mention too much about this. Just to say that by putting the similar problem together, you could reach speed up. You must be more interested in the moment because I don't have much time. I'll end at 12:30, is it? 5 more minutes. Okay. Let me just say that we also applied to UAV path planning, and we show that by solving two-copter problem versus a four-copter problem, these two-copter problems would help speed up the path planning for four-copter problem when I solve them together. So I won't go into this. Let me. Okay, this is the paper that I mentioned. Concurrently searching branches in software test generation through multitasking. The paper is currently placed online. So we'll basically try on software engineering problems, computation problems. In fact, also in neural networks. Because in neural networks, you have structures. A single layer network versus a two-layer network, you notice that there will be an overlap in that one layer between two problems. So you allow that knowledge to be transferred across. Let me just show you a simple example why it works. A very hypothetical problem. So you have two different problems in this case, the red one and the blue one. You can see that I define something known as local complementing. So I'll show you this point. Why is the red portion locally conflicting and the green portion locally complementing? You see that this red problem, in this region, the gradient of the blue function is moving up, whereas the gradient of the red function is going down. So in this way, you can see that they are locally conflicting. One is going up, the other one is going the other direction. Right? Similarly here, this is moving to the right, and this is moving to the left. This will be moving to the right, and this is moving to the left. But you notice that in region B and D, both are complementing each other. So in other words, if I have a solution here that helps it move in this direction, let's say based on gradient, it will help you move towards the direction that the blue function is also wants to move in. So you have a form of local complementing. Let's look at global complementing. You notice that for this red curve, it's moving towards this direction to the right. It is moving towards a direction that is nearer to the global optima of function 2. Sorry, of function 1. Right? Are you following me? So you see that if you drop a ball based on the gradient, where will you move to? You'll move towards here, right? This is towards the direction where the global optimum of the blue function is. Right? So in other words, this red function in region A and B is helping the blue function in finding its global optimum. Similarly, the region B, if you drop a ball, or rather in region B, if you drop a ball on this red curve, you also move towards, in this case, in this region, towards the global optimum of the blue function. That's why we call it globally positively complementary. So one of the functions is actually helping the search move towards the other function itself correctly. That's why it works. This is just one of the methods. I know I've gone much time. So this is also reported in the paper. I just want to conclude. So I presented a new form of paradigm known as evolutionary multitasking. And it's basically inspired again by how we multitask and how we know problems. So the key idea is by solving different problems together, we are able to solve them faster. Now, always imagine in the future, at the moment, if you look at a computer, we have a computer that multitasks for us, but in a way that the processors are all independent. I will expect in the future, our computer will make use of the knowledge for one problem to solve another problem. The data structure is completely different, such that you make use of data for different problems faster. So this is the key idea. So next more important thing is this. So as what Cassidy has mentioned, so we have a new journal. This is a new journal of the Computational Intelligence Society. It's starting in, the first issue will be in February 2017. I'm currently preparing it. It's known as the Emerging Topics in Computational Intelligence. Let me just give you some idea of what you should submit and what you should not. I have been as specifically told to reject those because we have our flagship journal, which is IEEE Transfer Evolution Computation. So if your work is solely on evolution computation, send it there. Okay? If your work is solely on fuzzy theory, send it fuzzy. If your work on neural networks and machine learning, send it there. But if your work is a very nice application of software engineering using any of those methods, send it here. So I would say this is a better value for you. Right? We like interesting applications. We like surveys. If you are able to write a nice survey on, I don't know, branch testing using computational intelligence, so this is the place. Okay? If you have new theories of computational intelligence, I don't know, maybe another black hole algorithm, I don't know. But I don't know whether it will be accepted. You can try. So we have 6 issues per year. It's an electronics only publication, so it's typically faster. And I try to keep my reviewers and my AE working hard by hopefully, if possible, in the current issue, I told them to get the review back by a month. Let's see how it goes. But for my case, it has to be a month because my first issue is in February. Okay, so again, I have 6 issues. per year. Ah, yeah. Cassidy has a special issue, he has mentioned it, right? It's in software,
Search-based software engineer.
search-based software, specifically your title. So expected in.
Yeah, the deadline will be early of November, so November 5th. And we try to give the notification of the first round on December 15th, so it's 5, to be able to have the special issue ready by April.
Yes. So I have reserved the April issue for. Okay, so I used to be the editor-in-chief of this journal. So because I'm the editor-in-chief of this journal, I cannot be editor-in-chief of this journal because of conflict of interest. But I was the technical editor-in-chief. So this is currently SCI index. Started in 2009. So we look forward to your submissions as well. And if you are interested in editing your own book, writing your own book, or have a proceeding published in this, having a proceeding published for your conference. So this is a proceeding for conference, and this is a book series. So you can let me know as well. If not, I know I don't have much time. I thank you. And I want to thank my team of people.
Thanks for visiting. It's very interesting talk. Any questions? Yes, David.
Yeah, I mean, you're right in a way. Because, I often look at optimization, especially population-based optimization, as a learning problem. Because for me, every population is a set of points, sample points. And you move from a set to the next set to the next set. So if you think about it over time, you have more and more data. You understand search space better and better. So all along, I have been working in the area of treating it as a learning problem. Surrogate is very much treating it as a set of data, learning from the landscape. And from there, I move on to the use of transfer learning in the context of optimization. In fact, I currently have a paper on autoencoder diffusion algorithm, which is currently under review. So I believe in learning from the problem and searching it. Because at the same time, I understand the problem.
Try to the same type of problem, and try different unification with them, because I think by combining them into specific data, whatever, you are actually introducing some type of either bias or constraint in the space where the solution can be.
It could be right. But I guess tackling different problems, just like how humans tackle problems. You will find abstract space. If you look at deep learning, I always like to compare deep learning and genetic computing. When means are defined as a building blocks. So if you look at deep learning, how it works, you have the raw data. From there, you get your first layer of features. It's a feature extraction problem. From that layer of features, you build the next layer of features. So that is a building block to the next layer. Which is the layer with the level of building blocks that you want to work with? It depends on the problem. Sometimes we want to tackle the problem from a very specific layer, sometimes a more abstract layer. But when you're tackling different problems that are different, you have to use a representation that's much higher. And that's how human does it. We do some form of abstraction. Otherwise, you can't find a common space for both. And knowledge from one problem would not be useful for the other. because you can't transfer that knowledge. Now, if I were to speak to you in French, there's no way I can teach you anything. Right? Right.
The first one, with the multitasking, is entirely as simple as you forget the problem one, you forget the problem two, if you wish. And then after you have to combine them.
Yes. It is as simple as that. So the key idea lies in the decoding. So at this stage, I'm using a very simple one, which is based on the random key encoding. This random key encoding has been used in combinatorial areas for a long time.
The real way is for complex model. Lots of done very good models and you tailor to make it, 4 or 5 stupid ones. And solve these stupid combinations parallel because they all provide insights for each other.
Well, it all depends on how you define stupid and intelligent. What is stupid may not be really that stupid because it's simple, it's just simple building block. If you think about it, if you think about how, how in biology, how life evolved, we all start from very simple genome, and from then we create cells and molecules. The example, they create more complex systems.
The cost of building a model with high veracity is very expensive. What you're saying is don't bother. Get a couple, if solving any problem is fast enough. In the past, we had a 50 build any problem. With those days, rather than spend all your time making $1 more accurate.
I don't think it's the same. Look, you see, I guess one of the things, as I mentioned, is that this is not a magical potion that can solve all problems. What I'm trying to make a point is that tackle problems that have high similarity. For example, as a software engineer, the kind of problems you tackle with is often revolving around software. Right? To be building a ship. So to speak, the problems that you tackle with have very high similarity. So in a way, when you solve the different problems together, we always say that this guy is an expert in certain areas. So there's this knowledge that he has acquired over years. So what I have also shown is that there could be problems that are very distinctly different, but yet you could leverage that knowledge. But I cannot guarantee that you always have this. But that's the key thing. So how do you then study when you get positive transfer versus negative? So that will be the key challenge.
Daniel, yes.
Yes. Yes. In fact, the functions are epistatic. The functions are epistatic. Combinatorial problems you can't. There's no way because the entire search space is very different. One is a binary problem, one is an integer problem. So the only way that I want to say is to find a search space that's common between the two. And that to harness that complementary brand is that. Because subset of genes is not good for the other task. The nice thing about evolutionary computation is you weed it out because of selection. Survival of the fittest. What is the worst case? If you think about it, intuitive, what is the worst case? Worst case, if I have a population of 100, worst case, if that two tasks do not help each other, what will happen? They will segregate into two subpopulations. Right? Because one subset of it is good for this problem, one is good for the other problem. So I would think the worst case is that they will segregate into two subsets of problems. At the moment, this is still an area that I'm trying to bring in more theory. I have another work that is published in SSCI, just to study, is it due to diversity? Because I once presented, and then Kayan Dad was in the audience. He was asking, is it due to diversity? In the context of multi-objective, yes, you want diversity because you want to find the entire Pareto prime. But in the context of evolutionary multitasking, it's not just diversity. In fact, it is because of this similarity between the two problems. It's helping it to converge rather than diversify. Because one of the subset of genes which is good for one task and happen to be good for the other gives you that free lunch. And as a result, that task also gets improved because of it. And it helps converge as a result for both problems. So it helps each other. It's just like if I were to collaborate with you and both of us are very good in certain problems, and we work on the problem together. So there's always this saying, it's better to have more brains, right? So to speak.
Yes.
So system transfer is implicit.
Yes.
How can we explicitly measure it?
One that, for example, I didn't get time to go through it. So this is one where we try to determine in this unified space whether one function is contributing to it. So we do some sampling of the function and see whether those points are contributing to one function to the other. So we use that as an example of the measure to do some tests. So we want to determine very often do we get more positive transfer versus negative. For example, these two functions. You can see that from these two functions, there is complete complementary, right? In this case, give you a 1. But again, I'm showing it on synthetic problems. So this is just one way at the moment. I'm still trying to do it theoretically in other ways. So when I shift it, there is no complete complementary, but you see the value starting, that one is complementing the other start to drop when you shift it. You shift it further, the complementary start to drop further. So this is one way to measure it in an empirical manner, sampling manner.
So maybe Carlos, you give your opinion about the many objectives. So my question is about: are we expecting to see many tasking instead of multitasking? Because it showed us some experiment with 2 tasks. So, but how about the scalability of the approach? Is it another problem to address the many tasking?
As tough as multi-objective in the context of many objectives. The problem of many objectives is you're creating another big problem over there.
But when you increase the number of tasks, you will increase the number of objectives.
But if you think about it, every task is just one simple objective in multi-objective. Actually, it's not that difficult as compared to many objectives.
Yeah, another question that we have is that why the multitasking work may be better than treating the 2 tasks, let's say, in 2 algorithms, where you try to learn some constraint from solving the first task, then after that using this constraint to reduce maybe the search space to run another algorithm. Of course, maybe the execution time would be lower using, but why it would work better than trying to?
I think one of the nice thing about this is, okay, as I always mention, one of the nice thing about evolution computation that we can always defend is that it's very simple. It's easy, it works. So this implicit parallelism is very powerful. If you think about it, it's just sampling based on survival features and so on. Of course, because of mutation. But one of the things that I always wanted to do also is in the context of mathematical programming, for example, which Carlos, for example, has shown simplex or complex methods, which are based on, in fact, multiple points in the context of gradient based. When you have multiple points, it's very much also population based. Think about it. So the probability that one of the points or one of the solutions is good for one of the tasks is higher when you have multiple tasks. So you think about it. The reason why it works is that when I have a sample, the probability that some of the solution is good for one task is higher because you have multiple tasks. Right? So you have a higher chance of hitting a better solution. And if it happens that a subset of solutions which you evaluate for just one task, you don't evaluate for all tasks. Okay? And that subset of solution is good also for the other task. What do you get? Free lunch. You and you are good on one of the problems, I don't have to work. You work. And vice versa. So as a result, you get this so-called improvement. I say there's no guarantee. But just like emo, there's no guarantee that you always have problems that are conflicting. Very often, some of the objectives do not conflict. If you put them together without knowing that they conflict, you might as well optimize it in a single objective manner.
Okay, great. So let us thank our speaker again for this great presentation. So Banana should be just on the top floor. So then at 2 p.m. we'll start the next session. Thank you.
Thanks.